Wait, 5 to double every year. Shouldn't it be 0.7? Fuck this. Can you type it in? Of course not. Well, okay, if it doubles every year, 5 times 2 to the 6, right? Which is 2 to the 6 is 64. Because the thing is, 0.7 is a little bit above log 2. If symploids die but not as quickly as they are born, and all. I gotta do this. I always check now in case I'm missing something. Because the thing is, on these, if it was Pearson, I wouldn't do it. But for this, it's like you kind of have to because you can't go back. and it's graded, but when the death rate is increased so that it's higher than 0, its value represents the probability that Simploid would die within a year. Simploids die randomly as if lightning strikes. Okay. Step the simulation 2 or 3 years. Uh, 2 of the birth and death rate combinations represent equivalent growth rates. Well, obviously it's the... Oh, see, this is what keeps... The problem with these pens is that they keep getting on me. That's the nice thing about the other pens. The other option is to use the strain of bacteria you have now, but boost production, cultivating bacteria and acquiring transport vessels. So when you first reach an oil spill, you can spread more bacteria. Basically what they're saying is, do you want to increase R or do you want to increase N0? If you developed a faster growing bacteria, how would this be represented in the model? A higher intrinsic growth rate throughout the time the population of bacteria growing on the oil. If you increased the production and brought more ships to how would this be represented in a higher value of N0? Which change will make the oil disappear faster? Well, okay, wait. Doubling N0. Well, it depends on the time, doesn't it? Can I give a list of functions? So obviously increasing the growth rate is better. Like even, yeah. A simulated oil spill is shown on the right. 2,000 metric tons of oil were spilled. Wait, 2,000 metric tons? Dude, that's a crazy amount of. If your oil spill cleanup organization claims that there is no difference in the effectiveness between using fast and what will you tell them? A larger number of bacteria at the beginning will consume the oil faster. Oh, well. I wonder if we get to do Lock of Volterra at some point. We did it in Diffie. Lock of Volterra is great. Very interesting model. I think it's periodic though, right? I forget. I actually forget like so much of my Diffie. Which of the following should result in a population reaching K sooner? Increasing the growth rate, decreasing the carrying capacity, and probably increasing the N0. Wait, actually, yeah. Let me see the first point at which it really hits it. And then at like 10 years. The confusing part is this. Oh no, it's starting to level off. I get it. Okay. So we're run, stop, remove 50. But why did it actually, this doesn't make sense because I think what happened is the carrying capacity went down to 150. So run, and we stop, and then we change it back to 300. Really? Globally, humans consume about 20% of all plant matter that grows on land each year. That's pretty crazy. Wow. That's pretty crazy. I would have guessed it to be lower. It's biased by the fact that like much of probably much of what is grown is controlled by humans. But the fact that we've out that's still pretty insane. Okay, these okay, this one was actually really fast. So I'm glad that this was fast because I have to do physics. A few plant-eating salamanders managed to float on a log to a large island in the Pacific. Which graph represents approximately how you might expect the salamander population to change over many years? At which point the plants that the salamanders prefer to eat are less abundant compared to when they first colonized them. I'm guessing that they're saying a logistic growth thing, but I don't. If you were modeling salamander population during the first few years, N is a lot less than K. You're studying the population dynamics of an algae species that recently invaded a lake. You measure the amount of algae in the lake at the time of the invasion. And then for 6 years afterwards, you conducted experiments showing this lake can support an algae population of 200 cells per square millimeter. Marked below is a dashed orange line labeled K. Suppose you are tracking the population size of a herd of bison inside a large protected park in the northern Rocky Mountains. I don't think there's really anything unethical with checking your work with AI. If you give it an honest attempt and then now you're just trying to like save the grade, like 2.9. That is just not true. Yeah, bro. I hate that we can't actually I want to go back and see if I think I'm done, right? That's the whole thing. Hold on, I just want to make sure that the dashboard doesn't have my shit on it. Oh wait, I can view my score, but can I view? You can view the score, but you can't. Can you go back to it? Can I go back to this thing? Okay, so you can go back to it and see what you got wrong. That's good. All right. All right, so that's one thing done. The next thing is now to read the physics book, do the physics problems, and then I got to do my lab report. My phone. Okay. All right. Waves. I have to do some engineering today too. I don't remember how far I got here. I feel like I should just go try to do the problems, right? Because I don't even know what the hell is going on here. All right, this is where I think I'm at. And I think that there's only 10 more pages to read. I'm probably going to try to get this book on my iPad and just read on the iPad, but whatever. Did I put the thing back on though? Okay. Oh wait, this is the wrong notebook. Okay, so this section is actually pretty cool. It's just weird. All right, so we imagine a pulse, and we choose. So this is a pulse. We choose inertial frame. Um, how do they phrase it? Moving along the pulse. Okay. So then we see uh what do we call it? Just elements, or we call them rope elements, string elements. Move to the left with velocity v. Okay, the string has tension T on it. If you increase the tension, and if you use a lighter string, so it should be F and H. Oh, what? Oh, here we go. F and H. Nice. Am I muted? No, okay, good. So G, do I have G? I had 20 meters per second for that one. Okay, cool. This is the tension. And yeah, okay, yeah. Good stuff. Whoa, this one's actually crazy. What the hell? When you calculate the tension, do you include the mass or the weight of the string? I doubt it. So then it should just be 150 G. Naively, but I don't think that's right because if this is a really good problem because we never really went over this in electricity and magnetism, but if the helicopter is accelerating upwards, then yes, we know the wave speed when we want to find the tension. Oh, right, right. Because the okay, I get it. Yeah. That's how you model. So the sum of the force we have is equal to F net, which is equal to the mass times the acceleration. The mass of the hiker and the sling, so that this is the 150 kilogram. So there's two forces on here. We have the tension force and we have the weight. So weight minus, or let's do tension minus weight is equal to F net, which is equal to the mass times the acceleration of the body. So the tension should just be, so then we're going to get T minus mg is equal to the mass times the acceleration. Dude, that's a great problem. So let me just restate the problem. So this guy gets picked up by a helicopter and he notices that given that he knows the length of the cable that he's being held from, if he flicks his wrist and sends transverse waves up to the helicopter and he is able to determine the time that it takes, then he knows the wave speed. Because the wave speed is the square root of the tension over the linear mass density of the string. And knowing the wave speed, um, so the real problem is then determining what the tension in the string is, because we don't know the tension in the string, and we don't know. So naively, if the helicopter was at rest or not accelerating, then the my me plus the sling's weight would be equal to the tension in the string because it's not accelerating. However, if you add those forces, you get the net force on me, which must be just by Newton's second law, the mass times the acceleration. So then you solve for the acceleration, uh, and you in terms of the tension, which inevitably ends up being the wave speed and the linear mass density. And we know the length of the string and the mass of the string. And V, we know V because we just know it has to be because I did this here. Because the wave speed times the time has to be equal to the length. And if we know it traveled that far, that's how we find the wave speed. All right, that's a pretty great problem, actually. Actually, that's a pretty good one. This person said, "Dude, who the fuck are you? Why are you on my timeline?" All right. All right. So 16.4. Let's do it. Let me get my jacket. It's getting cold. All right. When a wave or pulse travels from medium A to medium B, and the wave speed of in A is greater than the wave speed in B, um, and the tension's the same, then that means that the mass density of B is larger, and then inversion happens in the reflection. When a wave or pulse travels from medium A to medium B, and the wave speed of A in A is less than the wave speed in B, then and the tension is the same, then the density in A is larger. It doesn't get inverted. All right, so that's just kind of an interesting phenomenon. This is actually not true, right? God, okay. This is the thing that I hate about so far this physics class. Ton of like, there's just so much like, um, I don't know. It's just not as like strict. Or at least I wish they would say that, hey, like, you know, this is like a approximation. In addition to kinetic energy, there's potential energy associated with each element of the string due to its displacement from the equilibrium position. As the wave moves along the string, this amount of energy passes by a given point on the string during a time interval of 1 period. Therefore, the power or rate of energy transfer associated with the mechanical wave is the energy in one wavelength divided by the period. That's neat. That's pretty cool. That's a pretty cool derivation. The energy in a wave. I just wish that we could go into like without the approximations because like I'm not exactly clear on like how accurate this is. Like what if the amplitude is large? You know? I don't know. I don't know exactly what happens when the amplitude is large. I think the main thing was that the wave speed has a sine theta term in it or something like that. Anyway, so this is the power in a wave. Equation 16.21 shows that the rate of energy transferred by a sinusoidal wave on a string is proportional to the square of the frequency. Yeah, okay, that's good to know. The square of the amplitude and linear with the wave speed. In fact, the rate of energy transfer in any sinusoidal wave is proportional to the square of the angular frequency and the square of the amplitude. Which of the following, taken by itself, would be the most effective in increasing the rate at which energy is transferred by a wave traveling along the string? So the angular velocity is omega t is equal to 2 pi. So omega is equal to 2 pi over t. And so then increasing the wavelength doesn't change anything there. But v times a period is going to be equal to the wavelength. So then v is equal to lambda over t. So if you were to increase the wavelength, you would increase the wave speed. Now tension v is also equal to the square root of T10 over mu. Yeah, we need a different. There's tension and then there's period, and that's just gonna be annoying. It's got to be doubling the amplitude. So 16.5 D. Yeah. I was trying to figure out if they were being sneaky, but they weren't being sneaky. All right. So 16.5. We have mu is 5e minus 2 kilograms per meter. Is under tension with tench equals 80 newtons. How much power must be supplied to the string? Okay, so how much power? I'll have to do this derivation probably 2 or 3 times to get it. But of course, they just want you to plug in numbers like an idiot. If F is equal to 60 hertz and A is equal to 0.06 meters. Okay, so the derivation ultimately relied on dm over dx is equal to mu, and k is equal to 1/2 mv squared. So dk is equal to 1/2 dm vy squared. And this is vy squared. It's the transverse velocity, which is actually equal to vy is equal to partial y partial t, which I think was like minus a omega cos kx minus omega t. So that's the transverse wave velocity. And so then dm is just going to be mu dx, almost. And so then we're going to get dk is equal to 1/2 mu times, oh geez. Okay, this is going to be what, a squared omega squared cos squared kx minus omega t times dx. Is that really what they integrated? It's kind of a nasty integral. They simplified it because t is an unchanging. So we just... But was it this? It was 1/2 mu omega squared a squared cos squared kx. Okay, cool. All right, so now we get dk, or let's just say k is equal to 1/2 mu a squared omega squared integral 0 to lambda cos squared kx dx. And integral of cos squared, oh geez, that's a freaking nasty one. I don't know that at all. So we're just going to say ... k is equal to 1/4 mu omega squared amplitude squared times the wavelength. Okay, but then I don't understand what the hell this... I don't get what's going on here with the... For a wave on a stretched string, each little piece is tilted, so the string is slightly longer than it would be if it were flat. Oh, so maybe it is actually dx. It might actually be dx. For the mass density, the linear mass density. I'd have to think about that, but I think it actually is all good. So the key result is that the potential energy density is 1/2 times the tension times the square of the change in y with respect to x. Okay, so first let me just write down that. So the du is equal to 1/2 tension times partial y partial x squared dx. Okay, interesting formula. Yeah, okay. So first off, oh yeah, I hated this, dude. So the norm of the function, the norm of the gradient, right? That's what that is. I don't get this substitution though. Oh, yeah, they do. Okay. All right. So anyways, we get ds is equal to square root of dx squared plus dy squared. And then you can factor this out into dx times square root of 1 plus dy over dx squared. Bro, there's so many hidden... It's like, why didn't they put this in the book? Okay, so first we just... Basically, I'm just going to apply the equation. So the partial y, partial x... So wait, hold on. What do we have? We have a sine kx minus omega t. So to do this partial with respect to x, we should just get a k cos kx minus omega t. Okay, there, so I got that. So then, okay, so then we take the square of this thing and we plug it into, all right, so we're going to get du is equal to 1/2 tension a squared k squared cos squared, and then we're just going to do it as kx dx. And then you integrate this, and I guess you get... Oh, but wait. So T is equal to mu V squared, so we don't know the tension, I guess. So then we get a... And that V is the wave speed, not the transverse wave speed. All right. I don't know this one. But wait, actually I do know this one because we know that omega times the period is equal to 2 pi. So omega is equal to 2 pi over t. And then k is the wave number. And I'm not as solid on the wave number. I mean, I'm almost positive it's 2 pi over the wavelength, because then k over omega would be... Or no, it'd have to be omega over k then. Oh yeah, it's omega over k. Okay. It's much easier to remember the lambda over t and then work backwards, I guess. But it does a ton of math, and then we integrate, and we get that u is equal to 1/4 mu omega squared a squared lambda. And so it ends up being the exact same as the kinetic energy. So then E lambda is equal to K lambda plus U lambda, which is equal to 1/2 mu omega squared amplitude squared wavelength. Wavelength? But I thought it was wave speed. What did they do after that? Oh, power. Okay, yeah. Okay, so this is the energy, but then if we want the power, we just say that this amount of energy is E lambda is transmitted in one period, which is capital T. So then we're going to get, 1 over capital T times 1/2 mu omega squared amplitude squared lambda. And this ends up being, 1/2 something times the wave speed. Okay. So that's way better than just plugging in these numbers. But let's just do the problem now. Yeah, so the power is equal to 80 newtons. No, that's the tension. Yeah, I was like, what? Okay, so the tension is 80 newtons. The linear mass density is 5e minus 2 kilograms per meter. And the frequency is 60 hertz. The amplitude is equal to 0.06 meters. So yeah, so you're just gonna have to remember the formula for the energy in a single wavelength, because that integral with the cos squared, I'm not doing that. I'm not doing that. Unless I have a computer, I'm not doing that. So we get, it's 1/2 the density times the square of the angular frequency times the square of the amplitude times the wave speed, which is we'll just write as lambda over the period. So the period, which is actually equal to lambda f, because v is equal to lambda over t, but f is equal to 1 over t, so then v is equal to lambda f. So then we're just going to get 1/2 times 5e minus 2, and then the angular velocity times t equals 2 pi. So the angular velocity is going to be 2 pi over t, which is equal to 2 pi f. So it's really the square of the frequency here. So then we're going to get just 2 pi. And then we're going to get a squared, the amplitude squared. So this is 0.06 squared. This 2 pi actually needs to be squared also. Oh, but then this f also needs to be squared. So it's actually the cube of the frequency. Okay, then it's just going to be the wavelength. The wavelength. Do we know the wavelength? Oh, we know the wave speed because it's not just the wavelength over the period. It's also the tension, the square root of the tension over the thing. So this is going to be 80 over whatever 5e minus 2 square rooted. So then we can find the wavelength, because now this equal to lambda over the period. So it's just going to be 60 lambda. So yeah, so then square root, so 1 over 60 times 80 over square root of 5e minus 2 is equal to lambda. All right, so let's just start to get some of this stuff in here. So we have 10 bro, is 80 newtons. Mu is 5e minus 2. F is equal to 60. A is equal to 0.06. So now V is equal to square root of 10 over the mu. So this is V. So then lam is equal to V over F, right? Okay, that looks right. So now we have everything we need, I think. Let's just make omega. Omega is 2 pi over t, the period. So t is equal to 1 over f. So ohm is equal to, I could just write 2 pi f, actually. So that's the angular velocity. Yeah, that's the angular velocity. So I think we're good. We just write 1/2 mu ohm squared a squared lam f. P is equal to like 511 watts. Is that right? That seems wrong. Oh, nice. All right, we got it. That was pretty fun. I actually like these examples. I'm pretty locked in right now. Oh yeah, I forgot. I want to do this. Okay. I'm gonna go on a walk around the block, and then we're gonna do this section. Bro, I love these people that pop in and they're just like, gotta go, bro. Keep on the grind. My favorite type of comment. Actually, it's like my second favorite type of comment. All right, so linear wave equation in 5 minutes. Is it feasible to, like, does Apple and Google even allow for custom Bluetooth devices to transmit data? Like, one of the worries was going with the um, offloading the compute to a phone was that maybe those APIs are really inflexible and it would be almost as much of a pain to develop algorithms on those versus where even though compute is much less restricted because phones are extremely powerful, it would still be a pain just because of the developer experience versus developing on microcontrollers. All right, linear wave equation. Let's do it. Imagine undergoing an infinitesimal displacement outward from the right end of the rope element. All right, cool. We can do the problems now. And then I'll probably I don't know what I'm gonna do about the homework. I'll probably write the lab report, and then I'll start to like write up the homework for real. Write the expression for y as a function of x and t in SI units for a sinusoidal wave traveling along a rope in the negative x direction with the following characteristics. Okay. A lambda is equal to 0.8 meters. What was it? 3 sig figs, 3 sig figs. F is equal to 3.00 hertz. And y of 0, t is equal to 0. What? Why didn't they just write y 0, 0? And then, so that's A. B is write the expression for y as a function of x and t for the wave in part A, assuming y. I didn't see anything about phase offset. Did we do anything with phase? That's weird. Okay. Okay, so first off, K okay, V times period equals lambda. So V is equal to lambda over period, wavelength over period. Now, omega t equals 2 pi, and K lambda equals 2 pi. So omega equals 2 pi over t, and K is equal to 2 pi over wavelength. So then, so K is equal to 2 pi over 0.8. and omega is equal to so X is measured in meters. So it's going to be 2 pi over 0.8 meters times X minus omega, which is 2 pi 3 over seconds times T. This is in meters. This is in seconds. So then this is an angle. All right. So the second part of this problem is write the expression for y. Oh wait, but this needs to be a plus here because it's traveling to the negative x direction. How do you do this part? Oh shit. That was weird. Wait. Right? Yeah, that's definitely right. Yeah, because oh yeah, that's right. Okay. This is gonna be 0.080 meters. Meters minus 1 meters. All right, let's do this. Meters minus 1 meters. Seconds minus 1 seconds. What? It puts it in some random register? What? Yeah. Oh, yeah. A steel wire of length 30 meters and a copper wire of length 20 meters, both with 1 millimeter diameters, are connected end to end and stretched to a tension of 150 newtons. During what time interval will a transverse wave travel the entire length of the two wires? Don't we need to know the density of those? Because the wave speed is wave speed is equal to the square root of the tension over the linear density. So why does the diameter matter? Presumably because, oh, for real, this is what you have to use? The density of steel is 7.86 uh times 10 to the 3 kilograms per meter cube. And then the density of copper, 8.92 grams per centimeter cube. Okay, so we have the density of that. So now what we want to know is the linear, so now the volume per meter. So if this is 1 millimeter, then so then we're gonna have 1/2, or we're gonna have is equal to D. So then R is equal to 1/2 millimeter. So then pi R squared is equal to pi over 4 uh millimeters squared times, so then this is gonna be, so let's just write this out. This is pretty simple. So what was it, 27? But why is this coming after this? You gotta know. I'm pretty sure you have to know it, right? Is there another way? You need to calculate the wave speed, and the only way I can think of to calculate the wave speed is to find the linear density, the linear mass density. Um, all right, yeah, that's what it is. Okay, so rho steel is equal to 7.86 E3 kilogram per meter cube. Rho copper is equal to 8.920 E3 kilogram per meter cube. Okay, so the diam is equal to 1 millimeter. So then area is equal to pi over 4 millimeters squared is equal to pi over 4e6 meters squared. So then the volume per meter is equal to pi over 4e6 meters squared times 1 meter is equal to pi over 4e6 meters cubed. Okay, so then mu steel is equal to rho steel times vol per meter. Actually, this is probably the best way to do this. Is to write it as code. Actually, let's just write it like as normal code. It's a little bit more painful, but it'll run, and then then I only have to do it once. Okay, so that's a derived quantity. So V steel is going to be the square root of the, oh yeah, and the tension divided by mu steel. And V copper, square root T over mu copper. Okay, then T steel is 30, so L steel equals 30 U meter. L copper is equal to 30 U, or 20 U meter. So then this is just going to be L steel over V steel. T copper is equal to L copper over V copper. T is equal to T steel plus T copper. I should be able to just take this. What? Oh, that's the fucking worst. I hate that. I would make the parser way more, I mean, obviously that's the right way to do it, but that sucks. I don't like it. What happened now? I mean, that's obviously wrong. That can't be right because, wait, what did I just find? We found the wave speed of steel and the wave speed of copper. And we wanted to find the time. VT is equal to 30 meters, so then it should be like T is equal to 30 over V. But I got this. What did I say? Mu steel. Oh. Wait. I think that this needs to be a divide, no? Wait, what happened? Wait, row steel. Oh, because wait, this is supposed to be in kilograms per meter. So we have kilogram over meter cubed times, oh, meters squared. Yeah, I think that I think we're good here. So then this does need to be a times. This need to be a times. So now I think I'm good. What? Meters per second. How is this possible? This doesn't make any sense. T steel. T copper. How is it possible that if I add these two together, I get... What? Bro, what? How is this possible? Something obvious. So I'm missing something really obvious. Bro, what? Dude, what happened? It like didn't update or something? Like it like cached it? It must have like that was weird. Okay, whatever. Was that the right way to do this? Why would they offer me to download it if I can't even download it? All right, chill. 53. Ugh. Okay. A block of mass M is supported by a string rests on a frictionless incline making an angle theta with the horizontal. The length of the string is L and its mass is much less than the mass of the block. Derive an expression for the time interval required for a transverse wave to travel from one end of the string to the other. Okay, that's pretty simple. So, the tension vector is going to be mg sine theta in x and mg cos theta in y. And the way that the only way that I know how to remember this is, let's say that theta was 0. Which direction would the force point? Wait, this is the normal. This isn't the tension vector. This is the normal vector. The normal, and so I believe the tension should be the y component, right? So tension should be mg cos theta. And this is capital M. And then mu is equal to little m over L. So then V is equal to the square root of mg cos theta over little m over L. So L goes on the top. And so that's the velocity, but the time interval, so then we're just going to get L over V is equal to T, which is L times L divided by the square root of capital MG cos theta L over little m. Something like that. All right, so let me do this one. Okay, so we have N V is equal to mg cos sine theta mg cos theta. So then that means that the force in the y direction is going to be equal to the weight. I think so, right? Like, what else could it be? What am I blanking out on? Okay, so that means that mu is equal to L, or no, little m over L. So that, and V is equal to square root T over mu, and V times T is equal to L. And so then T is equal to L over V is equal to whatever. I mean, that's basically, well, let's write it out. So it's gonna be L divided by square root of mg L cos theta divided by m. I think that's it. Wait, if theta were 0, what? Oh, wait, that's true. Wait, hold on. How did I fuck that up? Hold on. If theta is 0, then the tension force is 0. Oh, wait. No, I had what? Yeah, the normal force will be entirely directed in y if theta is 0. Oh, yeah. Okay, I messed it up. Why would they have that? Oh my god. Oh, it's D. Okay. I wish the. All right, whatever. I was rushing. Okay, so I gotta do this lab report. There's one more, right? 63. These questions are easy. Like, conceptually, pretty straightforward. 63, is that what it is? Okay. Reducing the temperature, which results in a increase of the tension, taking the cross-sectional area of the wire to be blank, the density to be this, and the Young's modulus. What the hell? Why is she assigning this? We didn't even go over this. $373. I love when the PDFs sync the page number. That's like the best, man. Oh, I lied. Wait. No, wait. 373. What? 373. Jeez. Okay, so no, wait. What? Oh yeah. Five E minus 6 meters squared. Rho AL is equal to 2.7 E3 kilogram per meter cubed. And the Young's modulus is 7 E10 newtons per meter cubed. So what does that mean? That means that, what is it? So what strain, delta L over L, gives wave speed V equal to 100 meters per second? So we can kind of find mu, right? Because mu is kilograms per meter. So we just need to compute the tension, right? Wait, I don't actually know what the hell is going on here. All right, let's read this section. I actually want to know this stuff, but it's just like feels like now is not the time. Except for a discussion about strings in earlier chapters, we have assumed that objects remain rigid when external forces act on them. We explored deformable systems. In reality, all objects are deformable to some extent. That is, it is possible to change the shape or size of an object by applying external forces. As these changes take place, however, internal forces in the object resist the deformation. We shall discuss the deformation of solids in terms of the concepts of stress and strain. Stress is a quantity that is proportional to the force causing a deformation. More specifically, stress is the external force acting on an object per unit cross-sectional area. The result of stress is strain, which is a measure of the degree of deformation. It is found that for sufficiently small stresses, stress is proportional to strain. The constant of proportionality depends on the material being deformed and on the nature of the deformation. We call this proportionality the elastic modulus. The elastic modulus is therefore defined as the ratio of the stress and the resulting strain. The elastic modulus in general relates what is done to a solid object to how it responds. It is similar to the spring constant K in Hooke's law that relates a force applied to a spring and the resultant deformation of the spring, measured by its extension or compression. We consider three types of deformation and define an elastic modulus for each. Young's modulus measures the resistance of a solid to a change in its length. All right, consider a long bar of cross-sectional area A and initial length Li that is clamped at one end. When an external force is applied perpendicular to the cross-section, internal molecular forces in the bar resist distortion or stretching. But the bar reaches an equilibrium situation in which its final length Lf is greater than Li and in which the external force is exactly balanced by the internal forces. In such a situation, the bar is said to be stressed. We define the tensile strength as the ratio of the magnitude of the external force to the cross-sectional area, where the cross-section is perpendicular to the force vector. Wait, the cross-section is perpendicular to the... What? You mean... I hate when they do that because whenever I think of an area, I always think of its normal. But they're not talking about the normal. The tensile strength in this case is defined as the ratio of the change in length to the original length. We define the Young's modulus by a combination of these two ratios. Okay, so Young's modulus Y is equal to the tensile stress over the tensile strain, which is equal to the force over the area divided by the delta L over L. Okay, that's pretty interesting. Oh, so that force is going to be the tension. This is going to end up being the tension. Okay, so F is equal to A times strain times Y. And that's going to be in, so A is meters squared times strain, which is unitless, times Young's modulus, which is in newtons per meter squared. So yeah, so it's a force. So that's good to check that out. All right, so basically what we're going to get here is, tensile strain, stress, divided by the tensile strain. Stress is the force per area applied. Strain is the ratio delta L over Li. Okay, so then we can get that F is equal to, so I don't know if we're gonna be, F is equal to A area times Young's times strain, which is unknown. Oh, so wait, why don't we first find, okay, so V is equal to square root T over mu. So V squared mu is equal to T. Uh, so we should get V squared rho area is equal to area Young's strain. So then V squared is equal to 100 meters per second squared. Because what did we say? We said V. So then strain is equal to V squared times rho times area divided by area times Young's. I should just be able to. Wait, but the strain. Yeah, but that's what I want. Okay, what if I just pipe this thing into. .86 E minus 4. And it's a ratio, so that's it. I think that's the whole thing. Yo, who's here? Hi, bro. Found your channel. Oh, that's interesting. What physics? Sorry, bro. I'm here on the chat, Noir. Right now it's physics 3, waves, thermo, uh, fluids, and I think some other stuff. Um, but right now it's waves, and I just finished the homework. But I'm not gonna write it up yet because it's so boring. Um, but now I'm gonna do my uh lab report. Um, I might end the live just because I need to open up my email and stuff. But that's interesting. Wait, hold on. Let me read what you wrote again, bro. So you said, found your channel just now. I searched for computer science roadmap. It talked about something like lambda calculus, and I searched. She found me through that. Okay. That's pretty interesting. And it looks like that guy subscribed. So that's what matters. I actually hate that lambda calculus video because it's not even right. But people seem to like everyone seems to comment. They're like, actually, this is scheme. No, it's not. And I commented like 1,000 times. It's not scheme. Okay, so all right, I think I'm gonna end it. Um, I might eat now. I might make some pasta. I'm doing an only eat one meal a day thing. Okay, so I'm gonna eat, do my lab report, then do statics homework. I did the bio homework. Bro, having 4 classes is actually way harder than having 3 classes. I like having 3 classes because then you can like really spend a lot of time. But like right now, I'm in class. Let's see, like 6 plus 8 plus uh 5 plus 6. So what is that? 13 plus 12. I'm in class like 25 hours a week. Oh, wait, no. Plus, and then plus, well, kind of 3. It's like 26, 27 hours a week of class, which is just, it's like, I would prefer to have like way less hours of class and then way more time to just lock in. But so it goes. All right, so that's it. I'm gonna do this lab report and then maybe I'll hop back on later.